Okay, so welcome. Today we start talking about this new nowadays, but very new, let's say, field of machine learning, which is called generative AI. Usually it is called generative AI. Large language models are a big part of this new technology, generative AI. So today, in partially Thursday, we will try basically to understand better how they do the magic that they do. Okay, they are probably the technology that seems mostly magic that we see in this course. Partially, maybe also reinforcement learning at times seems a bit magic, but reinforcement learning is not very used in our everyday life. Instead, generative AI, I guess, it's much more used. So basically, we will start first of all with a quick, let's say, review of the history of natural language processing, because this field has a long history, well before large language models appeared, well before even neural networks appeared. And obviously it is a field of research that has been severely disrupted by this new technology. So we will try to do a brief, let's say, overview of the history of this field of research. Then again, quickly, we will mention a few approaches to deal with typical natural language processing tasks. Then we will shift to these new large language models and basically to try to understand better how do they work. Okay, so to try to understand that they're not actually doing magic, but they are actually doing something that is a clever combination of, in a sense, supervised learning and reinforcement learning. So basically, they combine two techniques that we already seen. We will focus on a specific way in which you can create the architecture in terms of the structure of the neural networks, because we will see that there are more than one neural network in the architecture of a large language model. We will focus on one specific of these architectures, so ways to organize a neural network, that is called the transformer architecture, because this was basically the big novelty that made large language models possible. Besides, along with technological advancements. So basically, the fact that someone, OpenAI or whoever, decided that it was a good idea to invest lots of money in hardware, okay, to train and utilize these systems. So one premise, one word of caution. The slides, I will publish the slides. I didn't publish them yet, just because I want to be sure that they are. Okay. The look and feel is a bit of a roller coaster. They have not the same layout as any other slide, because obviously to make these slides I assembled a number of sources, and because I was short on time, I didn't have the time to homogenize the appearance. So apologies, sometimes the font changes, the color changes. I know it's painful for the eyes, but bear with me, I will try to homogenize them during the Christmas break. Okay, so first of all, basically natural language processing is essentially a field of research in which we try to teach machines, or originally program machines to understand natural language. It's a very difficult task, because natural language is completely, let's say, different from what machines are used to. A programming language is usually unambiguous, specific keywords, a very limited size of a vocabulary. Instead, natural language is ambiguous, lots of terms with many different meanings depending on the context. So they are very different stories. So basically, approximatively, we can distinguish these, let's say, 6 big steps, eras, if you want, in natural language processing. Without too much imagination, let's call everything that was before 1990 the prehistoric era. Okay. Here, natural language processing was still a field of research. Okay. It was basically still bound to programming, explicit programming. We will see afterwards a few examples. Then around the year 2000, when neural networks were already used in many fields, recurrent neural network, which we already mentioned, without going to the details, but we already mentioned it to be a specific architecture of neural network that is able to remember information, came into the picture and advanced what we can achieve with natural language processing. More or less, take all of these dates as more or less. Okay? So more or less 10 years later, different derivation of recurrent neural networks were born to improve performance. So long short-term memory networks and gated recurrent units. We will see briefly, we will mention this. So don't worry. Then, in the last few years, let's say, in a few years, in the span of 3 years, a few different specific techniques come together to actually give us all the ingredients to transition up to now, basically, is the era of the transformer architecture. So, these specific, let's say, innovations were the notion of attention. There is a very famous paper in 2017, so this is actually taken as the year where transformers were born, which is attention is all you need. Paper in 2017. Obviously, we will see what is this concept of attention. So to get a bit better an idea of what happened in all of these years. So first in this, let's say, prehistoric era, this is what we can also call the symbolic era. When you say symbolic, when you see symbolic written somewhere, it usually means explicitly programming. Okay, symbolic because we program the computer through an explicit sequence of symbols, the keywords in the Python language, in the Python programming language, for instance, and the computer does not learn the meaning of these symbols. It has been programmed to know the meaning of these symbols. When we execute a Python program, there is a specific software in our computer installed, the Python interpreter, that understands the language and executes the instruction. So for instance, in 1954, so again, more or less when neural networks started to be proposed, in this experiment at Georgetown University, researchers tried to automatically translate Russian sentences to English. Okay, this was a very first, let's say, proof of concept. And then a famous system, which may be even in some movie, I think it has been mentioned, it's ELIZA in 1966. It was the very first chatbot. Honestly, it was a chatbot. You had a different interface, obviously. Most of the interfaces to a computer back then were textual interface, so you didn't have Windows and graphical user interface. But it actually was a chatbot. You can write sentences. ELIZA will more or less, let's say, understand and reply. Okay. It was extremely complex to program. Basically, you had to program syntactic rules of the given language you were focusing. It was English, the logics of a sentence. It was very, very complicated system. So chatbots are more than 50 years old, basically. They are not a novel idea. Then again, more or less in the 90s, data-driven approaches started to surface, okay? So the idea now was to actually not explicitly program a machine to understand language, but to use mostly statistical concepts, statistical machine learning. The kind of machine learning we have seen in supervised learning, unsupervised learning, nothing very different. So instead of hard coding, so programming explicit rules in the machine, we gave a given system a large corpus of text. What does it mean? A collection of documents. Okay. So an encyclopedia, if you want. We encode these documents in some way, we feed them to the computer, and then we hope that the computer learns something. We will see what. So here, for instance, you can find something that we already mentioned, like Bayesian approaches, support vector machines. Okay. And we will see a bit of how this worked. Then again, afterwards, neural networks were more or less already used in many tasks, vision tasks, supervised learning tasks. And traditionally, this era starts in 2013 because of another huge research paper that had a huge impact. That was the proposal to an encoding of text in a specific way. This was called Word2Vec by Google. This was a specific proposal about how to encode the text in a meaningful way for machines. Again, this is just an overview, okay? So we will go back to any of these details. This enabled the usage of neural networks instead of purely statistical approaches to learn not only the syntax of a language, but also the semantics. That is always the most difficult thing. The most, let's say, worldwide used languages, Italian, English, Spanish, German, French, they have very specific syntactic rules, okay? Usually with very few exceptions. So you can, let's say, easily encode these rules in a language. This is something that programmers know how to do. A programming language, in fact, think about Python or any other language you do know, is a language like a human language. It has rules, there's a syntax, a sentence must be well structured. So this is not the difficult part. The difficult part is telling a machine when machine means computer, when it means car, when it means an industrial machinery. Okay, that's the difficult part. So making a computer understand the semantics between the language. Nowadays, it seems that we became quite good in teaching machines to understand the semantics. So yet again, more or less until since 2017, with the introduction of this transformer architecture, large language models start existing. The term, just a quick look ahead, but the term large language models exactly means what it means. Language models existed more or less since when natural language processing existed. Okay, you build with statistics, you build a language model. Nowadays, models are large. They are huge models, and we will see what huge means. So basically, we have this first generation. Actually, BERT was the first, then GPT, more or less on 2018, and then nowadays we have generative AI at scale, ChatGPT, Claude, Gemini, many other, also apparently going well beyond the text completion and text comprehension, okay? Reasoning, stuff like that. So let's try to analyze a bit better some of these components. The natural language processes, as we said, is more or less the idea of teaching machines to understand and produce, hopefully, human language, okay, in whatever language. Obviously, the core challenge, as we anticipated, is ambiguity. Human language, whatever language you take, is extremely ambiguous. There are many different words that have the same meaning. There are many different meanings for the same word, and to disambiguate the meaning, you need to look at the context where the word appears. There are many implicits in language, okay? We don't use explicit subjects all the time. We use pronouns. Okay, so all of these, many words can be slightly changed depending on the gender of the subject they refer to. Verbs can be declined to different syntactic forms depending on singular, plural, whatever. Okay, so the main issue is ambiguity. But that's what natural language processes tries to do. So originally the main, let's say, experiments with natural language processing was about text classification, basically, or the one that were, let's say, more famous. Okay? Text classification may mean, for instance, to do sentiment analysis. This is something that is done nowadays. All of the, I would say, medium to big companies, especially working in marketing, in retail, whatever, do this. Pardon. Sentiment analysis means what are people saying about our products? So let's go on to social media. Okay, let's collect all the comments that tag a specific product, service, whatever, and let's try to analyze the comments that people write in natural language to understand whether the product is liked or not, basically. Okay. So, for instance, a very simple example could be check whether a given comment, Hugging Face is a famous site where you can find resources about machine learning. Put this comment into a text classification model and let the model tell me whether the comment reflects, okay, delivers, expresses a positive, neutral, or negative comment. Okay? This is the bread and butter of any modern marketing firm. Okay, you need to check. Imagine what happened to the sentiment analysis platform of Chiara Ferragni when the Balocco thing exploded. Okay, so not very good. Another typical task was question answering. This was actually the very first historical, because ELIZA was basically a question answering system. So we want to express a question in textual form and get an answer in textual form. Okay? So for instance, which name is also used to describe the Amazon rainforest in English? This is the context, and we want the output. Obviously, usually the context is not given along with the question, but the context can stem from a database of facts or whatever. Okay? Don't be surprised if, I don't know what you know about generative AI or how do you use it, but don't be surprised if many of these things nowadays can be done with large language models and generative AI. Natural. They are mostly dealing with the same problems. Okay. If you want, you can imagine a question answering system as a more human-friendly database query system. Okay. If you need to query a database, you need to learn, I don't know, SQL or whatever other language. It would be nice if you could query a database in natural language. So question answering systems before large language models, okay, this is not something that has been enabled by large language models. Before large language models, you could do this kind of stuff. In fact, the next question was, for instance, the so-called semantic parsing, so understanding the intention, the meaning of a text to carry out specific tasks. In this case, for instance, translate text to SQL. Okay? Again, this is something that could be achieved even before large language models. Are you familiar with SQL? Yes. Did you have some lectures, maybe in the, not in the master degree, but back? Basically, SQL, for those who don't know, is simply a specific programming quotes language devoted to querying databases. Okay, so you need to you can select. Imagine to have a big table. You can select columns from a given table depending on specific criteria. Okay, select all the products that have been sold for more than 1,000 euros, this sort of stuff. And then you get this data back from your data. Obviously, there are many other tasks, okay? Translation, obviously, is a big application area of natural language processing. One another that, let me see if I find it. Well, first of all, information extraction, name and entity recognition are similar. This means take a text, okay, and extract the meaningful information in some structured way. This, for instance, has been used extensively in medicine. In medicine, usually doctors take lots of handwritten notes. Okay, maybe nowadays they have iPads or whatever, but not many years ago and still today, doctors take a load of handwritten notes. Okay, turning the notes into structured information is meaningful and useful for a number of reasons. Okay, so that was another. And another, let me see if I find it, otherwise I will tell you anyway. Just if I can find it. No, I don't find it, but maybe there is somewhere. Another huge application of natural language processing principle is so-called argumentation mining. Argumentation mining is finding claims in text, in plain text, in natural language text, an automatic way to find claims, to find arguments and their premises, okay? And even if this seems abstract, one of the applications of argumentation mining is, I think that nobody here reads the terms and conditions of the stuff we accept, okay, online. So actually, one of the tasks you can do with argumentation mining is check those terms and conditions automatically and check whether they contain contradictory text. Okay, so you have the right to own your own images, whatever, and then after a few thousand lines of text, all uploaded material belongs to Meta. No, they are in contradiction. This is a huge deal, okay, because if in a contract there is a contradiction, you can tell that the contract, you can say that the contract is not valid. Okay, so this is a huge application. And then you can also check whether the terms and conditions of any given product, service, whatever, complies, for instance, with the law of a specific country. So argumentation mining, for instance, is used to try to automatize the way we check basically the law. not only the Italian law, but in general, laws are written in natural language, and there are lots of scientific papers, articles that basically analyze a given corpora of laws in a given country and find out that laws were even contradicting each other. Okay, so that's another field. So now, okay, how we can do all of this? No? We can do all this fancy stuff. So now we will try again to overview some of the techniques. So first of all, usually the first step in our journey to making a machine able to understand text is tokenization, is so-called tokenization. So we need to break text in smaller units that we call tokens. The easiest mapping you could imagine is taking individual words. Okay, so that's easy. Any kind of text, I can decompose it into individual words. We will see that it is not actually exactly like this, but that's a good approximation. Okay. So, for instance, we have the sentence "I love AI." The sentence is composed by 3 tokens: "I love AI," and these tokens obviously can participate in many other sentences. All the set of the tokens forms the vocabulary of a given language. Then this is, let's say, nice, but we still have the problem that computers don't understand the words. Okay, they only understand 0 and 1s basically. So we need to encode words in a way that is at the very minimum can be understood by a computer. That's the very minimum, the bare minimum. But hopefully we also want to perform an encoding, so a translation of these words in another representation understandable by a computer in some meaningful way. So for instance, the first translation that we can think of, one-hot encoding, that is something we already know. So the idea is simply create a fixed length vector and only one bit is flipped to 1. That's a very easy translation, but that's also very inefficient translation, meaningless translation. If you take, I don't know, the Italian vocabulary, you end up with very huge vectors with only one bit to 1 and with no semantic meaning whatsoever. One property of one-hot encoding is that every term that you represent with one-hot encoding is completely orthogonal from one another. They are equally distant. Every term is equally distant. They only have one bit at 1, all the other at 0. So you lose any kind of capacity of ability to attribute meaning to a word. The distance between apple and banana will be the same distance between apple and the White House. That's obviously not what, as human beings, we envision. And we will fix this issue later on. We said that usually we don't really tokenize a sentence into words as we humans intend them. Usually we do also stemming and lemmatization. We know that in mostly any language, a given word can be slightly changed depending on gender, plural or singular, stuff like that. So stemming and lemmatization takes care of this. Okay? So running and run and runner, okay, they are the same concept basically. It's the same word that is slightly changed depending on the context, the role, subject, verb, okay. Cats is the plural of cat. I don't want to encode these 2 words as 2 completely different words. They are the same words, but they are slightly changed to accommodate the grammar rules of a specific language. So basically this is stemming technique. You try to remove the declination of a word and only take the root if you want. This is very easy and fast to do. The problem is that you incur the risk of producing non-words. So if you cut, sometimes you can't keep the root, have the root being a meaningful word. Okay, sometimes you need something else. Another technique is lemmatization that uses the whole vocabulary and some grammar rules, so morphological analysis, to return some, let's say, some basic vocabulary. So for instance, with both stemming and lemmatization, running will be reduced to run. But for instance, better in stemming will be not reduced to anything. Instead, with lemmatization, you may reduce better to good. Better is a measure of quality. You could do something like that. This is much slower because you need to do much more accurate analysis. Here, you just take one word and cut it with some criteria. Here, you need to look at the context where the word appears. So this is slower, but it's more accurate. Okay? So this is actually what you do. You don't simply take words. Then other things you could do, and this is all of these things exist again since well before large language models, and are usually part of, let's say, a natural language processing pipeline, are part of speech tagging and dependency part. Part of speech tagging, also abbreviated in POS, basically tries to link words with grammar. So they attach to words some metadata, okay, telling to the computer, in this case, what is the role played by that word in that sentence. So for instance, part of speech tagging may enrich words the cat set with metadata telling us that the is a particle, cat is a noun, and sat is a verb. Okay. How do we do this? Not something that we will investigate, but you don't need basically large language models to do this. You can do this explicitly, programming explicitly, compiling a list of verbs, of nouns, of whatever, or you can try to learn this. And dependency parsing, instead is trying to understand the dependencies between words. So for instance, the fact that the verb refers to this noun, okay? Or if we have a complement, what is the reference to the complement, okay? If we have adjectives, what are the adjectives referring to in the sentence? Okay, so this actually builds some sort of a graph of a tree linking words together, okay? Usually in dependency parsing, we identify so-called head words, so words that to which other words refer to. So one head word could be a noun, okay? And the noun can be linked to adjectives, to verbs, stuff like that. So now that we took a piece of text and took every sentence, tokenized words, and then further reduced words down with lemmatization or stemming or whatever. How do we represent a whole document, okay? Well, one of the easiest representation is the so-called bag of words. A document is just a collection of words, of tokens. This is very simple. Simple usually means fast to compute, efficient to store, whatever. The problem is that we lose many different and relevant information about the original text. A bag of words technically is a set, which means that that is a disordered collection of words. Okay, So first, you already lose the order of the words, and we know that any language has its own rules, okay? By losing order, you also lose the context. Every word is represented individually. But it's very simple. Basically, you can imagine this representation of a document as a huge histogram. Okay? You put into the x-axis, so horizontally, you put all the words, and then your bars are how many times that word does appear in the document. So very easy. But again, lots of meaning is lost. A slightly better representation, respect to the bag of words, is so-called TF-IDF, term frequency inverse document frequency. I wasn't sure about the second part. This novel representation starts from a very simple idea. Not all the words are equal, especially in the context of a document. We can imagine that in any language, some words do appear a lot, regardless of the nature of the document, whether it is a medical bill, a programming language, a website about tourism. Okay, there are some words simply that appear a lot. Why? Well, for instance, articles. The, a, we can expect those words to appear a lot, and, or. But oftentimes we can generalize and say that the more a word appears in a document, the less information that word gives us. Think about this. Articles carry very little information. If we want to understand what a document is about, we don't really care about the articles. We don't really care about the pronouns, the conjunctions, okay? All of these particles in text. We don't really care about them. But we can expect in the histogram to appear a lot. This is connected to entropy, okay? If we remember when we mentioned entropy. If a piece of data recurs a lots of time, it has low entropy. It doesn't really tell us much, okay? Instead, things that are rare, they tell us more. If I'm comparing documents from the healthcare sector and documents from the IT sectors, I can expect that all of these articles, particles, carry very little information. I can expect to have more or less the same frequency of the, both in a medical or in a computer science document. Instead, in a computer science document, I can expect to have words such as machine learning, whatever. In a medical document, no, not so much. So, rare words actually likely carry most of the meaning in the context of a document. So basically, in this TF-IDF representation format, what you do is that you assign to every word a score that is computed by multiplying these two separate terms. The frequency of a term, so how often a word appears in a document, okay? It can be a raw number, it can be a percentage, we don't care. We just care about the concept. Multiplied by what? The inverse document frequency, which is in this given document, this term, this word, this token appears 10 times. Okay, but what is its frequency of appearance in other documents? Just an intuition. If in this document the words appear in 10% of the text, but if we consider all of the documents, that term only appears in 1% of the documents, I can safely say that for this document, that term is highly relevant, right? If instead a term appears in 50% of my documents, already that term is not so meaningful. Okay, it appears more or less everywhere. So this is a very clever and simple uh, representation that can tell us something more about the relevance of terms. Only the relevance. Nothing about the meaning, the semantics, okay? We only can say something more about the relevance of the term. We just said we can say something more only about the relevance. We can't say anything about the order. We can't say anything about the context of words. So another idea, and then if I remember well, yes, we more or less stop. So another idea in, let's say, traditional natural language processing was not to only represent individual tokens, but also groups of tokens. And this is the idea of an n-gram. Okay? You can have a bigram, you can have a trigram, you can have a fourgram, whatever n you want. The idea of an n-gram is simply do not use single tokens, a unigram, that will be, but look at sequences of words. If we want to tokenize New York City, okay, up to now, our tokens will be New York and City. Three different terms, and we are not able to connect them together. We lost their connection. If we switch to a bigram, we can keep New York. That's better, okay? If we could keep a trigram, we can keep New York City. Maybe this time is not so meaningful. No, New York is probably New York City. So obviously one could say the more that we can keep, the better it is. Obviously the problem is that if you keep more words together, so if you increase n, obviously the size of the vocabulary explodes. Okay? So there is a trade-off. Yeah, keeping more tokens together gives us better information, but also the size of the dictionary explodes. So here there is a trade-off between how much information we want to preserve and how much memory do we have, for instance. Okay. Based on this representation, so TF, EDF, n-grams, whatever, let's say the classifiers before deep learning actually became a thing were mostly of two families. A Bayesian family approach, an approach here is called naive Bayes. This is a probabilistic classifier. Basically, you apply the Bayesian theorem, okay, to try to predict the probability of seeing a word given another word. So the Bayes theorem gives us the idea of conditional probability, so the probability of an event given that you observed another event. You can use this formula in a naive Bayes classifier to try to predict the likelihood of seeing any given word given a collection of other words. So if we think carefully about this, what you are actually doing with naive Bayes classification is estimating the probability of co-occurrences. How it is probable that these two words appear together in a sentence, that's all you can do. Again, you don't have a notion of order, you assume independence between words. That's a big issue. We know that words in a sentence are not independent from each other. On the contrary, they give context to each other. But it is fast, effective, and basically before deep learning, it was everything we had. Another approach could be logistic regression. Okay? This, for instance, is used even in spam filters. It was used. A typical natural language processing pipeline we described so far is like this. To clean data, okay, let's assume that the documents we want to play with are taken from the web. We need to clean the data, okay, because if we take a web page, probably we have some noise, let's say HTML tags, all the special characters, for instance, punctuation in this kind of approach is completely meaningless. We don't represent punctuation at all, even if punctuation has a role in a sentence. For instance, understanding whether a sentence is a question or not. We completely forget about punctuation. Then we tokenize, we remove stop words, so meaningless words, we do stemming. We represent, so up to now, we are not actually representing words in a way that is understandable by a machine. Then instead we need to do so. And finally, we try to train our model or use our Navi base, whatever. Lots of libraries to do this, okay? And LTK is actually the ancestor of all of these things, okay? It is probably the most well-known natural language processing library. Just a few examples. Here we are going into the generative AI stuff. So let's do this transition. So we already highlighted a few limitations of these approaches. So let's try to understand how do we move from, let's say, pre-neural networks, natural language processing, to post-neural networks, and then LLMs. So a first issue that we already mentioned, and probably one of the most important ones, is the so-called curse of dimensionality. So in all the methods that we have seen, the size of the vocabulary, so the size of the tokens included in the language we want to model, determines the size of our representation. Okay. And the problem is that in this representation, most of the information that occupies space, memory, is 0. Think about one-hot encoding. Okay. But even with TF, EDF, it's the same. You have a huge matrix, you can imagine, with one term on the rows, and in the columns, all of the documents in your training corpus. Anytime that term does not appear in one document, that cell of your matrix has a 0, whatever representation you choose. So you are wasting enormous space. Okay. Other issues that we already mentioned, you have no notion of semantic similarity. With one-hot encoding, you have basically nothing. With the FDF, at most, you have some notion of relevance. With engrams, at most, you have some notion of order and or context. But you still don't have a usable representation of meaning, okay? Again, what I was saying before. Bank may be the bank where I deposit money or the bank of a river. Okay? Either I store the complete sentence or I don't have any clue about what is the meaning of bank in a given sentence. Okay? So we need something better. As we anticipated, in 2013, another representation came out called Word2Vec by Google that had a very, very interesting property. And if I remember well, it was quite a surprise also for the authors because they tried, they didn't really expect to work it this to work it to that this thing will work, but it worked. So this word-to-vec representation that we don't really care about now, but we will see, simply associate a vector, okay, of a given size to a word. So a vector of number, okay, floating numbers, bytes, we don't care. Each word is associated to a vector. This vector is constructed in a way, this vector actually is not constructed, we are in 2013, so this vector is actually learned. Is some representation, a neural network learns to represent a given word with, I don't know, a sequence of floating point numbers. We don't know why. Okay? This is something that the neural network learned by feeding the neural network with lots of examples of the word used in different contexts. The interesting thing that they noticed is that with these learned vectors, they could do basic arithmetics. So they noticed that if in the representation of a word king learned by the neural network, so we take word king, we ask for the neural network for the representation of word king, that we don't know why it is made in such a way. Then we ask the neural network for the representation of word man. We get two vectors, no? Numerical vectors. We subtract the two. Just something that, I mean, strictly speaking, for a human being, subtracting or adding words doesn't have any sense. We subtract from the vector representation of word king the vector representation of word man, and then we add the vector representation of word woman. The vector representation that we get back, if we check what's the most similar word, okay, in the neural network representation of the vector that we obtain, the word that we get back is queen, which makes incredibly sense, right? The king is a male human being, I don't know, head of a government. We remove man, we add the woman, we want a female, okay, human being, head of a government. And this is extremely powerful. Now we can say that somehow, somewhat, okay, we don't really know how, but somehow the neural network is understanding meaning. Or at least for some, here we also enter into philosophical things, okay? And nowadays, obviously, the debate whether LLMs are able to reason, to actually understand the semantics is heated, but maybe saying that the neural network understands meaning is too much, but what we can say for sure is the neural network learned a representation that somehow, to some extent, preserves meaning, is able to associate words with similar meanings. Okay? Again, we know a little bit of neural networks. We have seen the surface of how they operate. It's not magic. Okay? We feed lots of examples of text with there is a king, maybe some articles, adjectives, indicating that the king is a male, okay? Then there are lots of text with queen, with nouns or whatever, indicating that queen is a female. Then maybe there is a lot of text in which queen and king came together, okay? So that's what neural networks do. They approximate any arbitrary function, and here very difficult to formulate a mathematical function, no? Like, I don't know, an hyperbole or whatever, a polynomial or whatever. This is a completely arbitrary function, discontinuous function, but the neural networks after being fed with several examples, apparently learned that there is a relationship between all of these terms. That is what the neural network learned. Okay, if you want to take a skeptical stance, okay, so let's be skeptical. We don't believe that neural networks understand the meaning, but we must nevertheless believe that the neural network learned that these four terms are related. If I swap queen for king, and we swap the signs, probably the neural network will give another correct result. Okay, so that's what we must admit, even if we are skeptical. So this vector notation is able to actually represent several different semantic stuff. For instance, space. With such notation, okay, and just to try to understand what's behind this vector notation, no? That we didn't actually explain yet. Let's adopt this analogy. Washington DC is a city and there's a place on the map, okay? Let's imagine a bidimensional space. You have a latitude and a longitude. Given the latitude and the longitude, you can do spatial reasoning. You can say that Washington DC is near New York. And for instance, it is instead far away from London. Okay? By looking at terms, you cannot say this. You can say this if you look at the coordinates. Okay? That's basically the analogy. Okay? The vector representation here is some representation that includes some form of, for instance, spatial reasoning, but not only spatial reasoning. It has been seen that this representation, again, proposed by Google, captures a lot of semantic information. It is able to understand opposites, man and woman, good and bad, okay? It is able to understand plurals without we teaching them. It is able to understand gender, okay? So basically this learned representation is able to understand all of these relationships. A mouse is to mice as a dollar is to dollars. The notion of plurals. Okay. Maybe if you ask the neural network what a plural is, the neural network cannot give you an answer. But the neural network learned that these things are as related as these two things. As related as means the vector space representation, the representation that the neural network learned, actually the distance between man and woman is the distance between. That's what the neural network learned. Okay? Obviously, if you're curious, you can check actually the paper or main explanation there are on the web, and I put in the slides from time to time some reference link. So how did Google did this? Google used at the time Google News was a thing. Nowadays I don't think so anymore. But Google News was basically a summary of news, okay, made by Google automatically from the web. So basically Google trained this word2vec model on Google News. It was its own information. It has access to it. Each word is represented by, I don't know the exact number for word2vec, but could be easily hundreds or even thousands of dimensions. So don't imagine a vector space with 2 dimensions, okay, like here. Likely there are thousands of dimensions. For instance, in GPT, that is the original model behind ChatGPT and others, I think it's like 12,000 something dimensions. Huge space. You have this model learned the relationship between the biggest and smallest. Okay. What the neural networks are doing here is so-called representation learning. They learn a given numerical representation of words with some properties. Okay, depending on what? Obviously, depending on what was the goal of learning. Okay, whenever you train a model, as we have seen with supervised learning, with unsupervised, with reinforcement learning, even you have a goal. Okay, you want to minimize the error, you want to maximize the expected reward, you want to do something. Actually, an evolution of word2vec is called globe, but we don't go into the details if you're curious. Basically, word2vec has only one main limitation, that it relies on a local context. So to assign the representation to a word, word2vec looks at nearby words. Globe is an evolution in which you can also look at the global document in some way that we don't have time to uncover here. Okay? So again, this was a huge novelty, okay, a huge result from the research in this topic, because this was the first time in which, when a human being looking at what the output of the neural network was, could actually be convinced, be persuaded that the neural network understood the semantics of it. Okay. Now let's do a first pause. After the pause, we will start to see the role of advanced neural networks to surpass even the limitations of the word2vec representation.